Hey everyone, this is the first geometry video, lesson 2.1. This would have been the lesson that we would have done this Tuesday, September 3rd. However, because of Hurricane Dorian, we're not going to be able to do it here. I'm not going to be able to do it in front of all of you. So this time you're going to see a bunch of small videos of each lesson that would have been covered on Tuesday. And we're going to start off with lesson 2.1. Now be mindful, this is a new chapter. So you may be seeing some new things. However, some of the concepts do relate back to the lesson, to chapter 1. Now, before you actually get into this lesson, please make sure that you do the chapter 1 test. The chapter 1 test was due this Tuesday, the 9th. However, because of Hurricane Dorian, it will now be due September 10th. So no need to email me the test or forward it to me via study place. All you need to do is just make sure you and your child or whoever is listening to this, right, make sure that they bring you bring your test next class. So we're going to start off with lesson 2.1. If you don't have your textbook, I recommend you get there. Also, there are some printed notes that I will be referring back to. However, I don't have the printed notes necessarily printed out, and they won't be in front of you. I will be writing out the examples of the printed notes here on this piece of paper. So those are the things that you're going to need for this lesson: textbook, something to write with, and section 2.1 notes, okay, which are online on Study Place. Now, lesson 2.1 is about inductive reasoning and conjecture. Might be wondering, what is that, Mrs. Elliott? Well, luckily, right there at the top of page 78, there's two highlighted parts. One of them being what a conjecture is, and the other one being inductive reasoning. So I'm going to read what a conjecture is. A conjecture is an educated guess based on known information, meaning that you can make educated guesses from information that they're going to give you ahead of time. Okay, kind of like a prediction, if you will. Now, inductive reasoning is reasoning that uses a number of specific examples. So now they're not just giving us information, they're giving us examples to arrive at a plausible generalization or to arrive at some prediction. Now, you will see throughout some of the examples here, right, that they are going to use, and throughout your homework, they're going to use things like make a conjecture, determine the inductive reasoning, and even some other future vocab words that we're going to emphasize on in a bit. But first, we're going to actually look at page 78, example 1. I have my textbook here next to me. You're not going to be able to see it to the best of your ability. So obviously, go look back on your textbook. Don't rely on my textbook. But as you can see here, there are, right here in example 1, it talks about patterns and conjectures. And the statement here, it says, for example 1, the numbers represented below are called triangular numbers. Make a conjecture about the next triangular number. So here's the thing, we have 1 dot here, 3 dots here to make a triangle, 6 dots here to make a triangle, 10 dots here to make a triangle, and 15 dots to even make a larger triangle. And as it mentions up here, the statement or the question that they're asking you, what the work that they're asking you to do is make a conjecture about the next triangle. So the next triangle, meaning we have to make a conjecture or make an educated guess about my next triangle. Well, we have the information, this can also be seen in the textbook, that in the first image, there's only 1 dot. The next image, there's 3 dots that make a triangle. The next one is 6, then 10, then 15. Okay, so there's obviously, the triangles are obviously getting bigger. So ideally, this next triangle, right, needs to be bigger. And it says make a conjecture or make an educated guess about this next triangle. Maybe they want us to figure out how many dots this next triangle would have. So first we need to realize, right, the information that we have. We need to see maybe if there's a pattern, if there's something and a conclusion that we can come to maybe help us get our conjecture or our educated guess. So from here to here, from 1 to 3, that goes up by 2. If you want to write times 3, that might be another thing you're looking at. For now, try to see any pattern that you possibly can. So right now I see this goes up by 2, From 3 to 6, that goes up by 3. From 6 to 10, that goes up by 4. From 10 to 15, that goes up by 5. And hey, that's kind of a pattern within itself. 2, 3, 4, 5. This next one, the conjecture that we can make, which is how we write our answer, the conjecture we can make is that the next triangle will increase by 6. Obviously, if this is 2, 3, 4, 5, this is going to increase by 6. And it would kind of look like this, just doing 15 plus 6, which is 21. So that was our conjecture. It was kind of a statement. It wasn't just giving the number 21, but explaining what's going to happen. What was your educated guess? What was your thought process behind this? So it's pretty much a statement more than just writing it out, okay? So that was page 78. That was example 1, okay? We're gonna do example 2 on the next page. So if you go to page 79, example 2, that's what we're gonna do next. I'm gonna bring out the textbook here so you can see the question. I am gonna kind of rewrite the question, but as you can see here, it says that there are, I'm gonna try to turn it sideways for you guys. It says 4 points, for points, not the number 4, but for points PQR, okay, so there's 3 points, PQR, PQ equals 9, meaning there's a distance of 9, QR equals 15, and PR equals 12. Make a conjecture and draw a figure to illustrate your conjecture. So they want you to draw something now, not only just make the conjecture, but draw it out. So let's see what that would maybe look like, okay? So let's sum up what we just read. So we just read that PQ, we just read that PQ has a distance of 9, QR has a distance of 15, and PR has a distance of 12. And like I said, we got to come up with any statement that we know is basically an educated guess about any of these, right? Well, they give us these distances, and honestly, maybe you would think, can any of these be collinear? Can any of these points be collinear? Meaning, can any of them lie on the same line? We talked about that right in the very first lesson, what collinear is. So collinear, basically, can I have 9 and 12 or PQ and PR and that equal QR? Let's see if you can see what I'm talking about. I'm going to write it out. If I had PQ and I add it with PR, right, can that equal QR? So PQ is 9, PR is 12, QR is 15. Can that equal each other? No, they can't. Meaning that they are not collinear. Not collinear. Mrs. Elliott, why are you wording it like this? Well, if you think about it like so, if I wanted to make dots, right, maybe put P in the middle, put Q over here, put R over here, there's no way that all 3 of them can land on the same line. Yeah, we know that from P to Q is 9, we know that from P to R is 12, but this does not add up to 15. Okay? So that's how you know if something was collinear or not. You would kind of set it up as 2 segments adding each other to equal your largest segment. So if they're not collinear, the conjecture we can make, okay, is literally writing out, okay, P, Q, and R, or points P, Q, and R, are not collinear. But then it specifies in that, on that page, that not only do they want you to give a conjecture, they want you to draw or illustrate something that would not be collinear, right? You want to kind of represent what you're saying. So if they can't be on the same line, maybe that there's 3 separate lines. So we're going to start off with maybe PQ, and I'll put PQ like this. Now, you don't have to, I'm not doing it exactly the way that it's drawn out in the book. You have your own version to draw out. I'll kind of find it suspicious if everybody's drawing it the same exact way. You know, I don't think, 20-something kids think that much alike. But PQ, okay, can represent 9 units, okay? QR, or maybe we can do QR, can be 15, and then PR, which is right here, can be 12, okay? So this could be an example of a triangle that you draw, okay? There's many other triangles that you can draw that you can, move the letters around. But as you can see, none of the points are collinear because there's 3 separate lines. None of them can be on the same exact line. I can't have an R here or a P over here or a Q over here, because then that's just not going to follow what we just did up here. So we were able to do the conjecture, and we were able to determine that they cannot be collinear, okay? Okay, so now what we're going to talk about is a counterexample. I'm sorry if the video looked like it jumped. It did. I had somebody from my family wanting to talk to me, so sorry if it kind of jumped all of a sudden. But a counterexample you will see on your printed notes. I don't have the printed notes here. I recommend you print it out, okay? And you take a look at the definition that I wrote here, as well as the examples that I'm going to write out, because they're basically going to be the same examples from before, okay? From the printed notes. Now, a counterexample, we know what an example is, but a counterexample, the basic definition is you must keep the given statement true, but the conjecture false. Maybe you might not know exactly what that means, but sometimes they're going to give you a given statement, and this time, instead of making your conjecture, they're going to give you a conjecture, okay? And you need to determine if the conjecture will always be true or if there's a counterexample. Maybe there is a false example, an example that you can tell that the conjecture will make it false. So just before I even get into this more, let me just show you an example to show you what I'm talking about. So let's say they give you a statement, just like how it is on the printed notes. They give you x squared equals 16. And in the conjecture, they tell you that x equals 4, right? This might be something that that somebody gives you, and this is a conjecture that you make. You're able to determine that x can equal 4 here. However, we can actually apply what we call a counterexample if we think it's possible. Now, this is not always possible. It's only if we think it's possible, okay? Meaning, is this statement only true, or is it false, right? So first off, we need to determine, is it true or false? If it's true, no need for a counterexample. If it's false, then we need to write out why this conjecture is not fully true and why it is false. So a counterexample would look like this. Well, even though x can equal 4, right? Because 4 squared is 16. Actually, this statement is false because there is another number that can equal x. So false because x can also equal -4. So what does that mean? Well, if I plug in -4 here in the given statement, -4 squared also equals 16. So even though this is partially true, it's not the full truth, which is why our counterexample, we would say that it's false because x equals -4. And that's where this definition comes in. You must keep the given statement true, meaning we must believe that this is true at all times. However, we got to make sure that if the conjecture is false or not, okay? So if you're hearing rain in the background, by the way, it's obviously raining because of Hurricane Dorian. So don't mind the rain in the background. Let's actually keep going with the next given and conjecture statements that they give you here. And maybe I will give you one to think about at the end that I'll make up on my own. okay? So the given one that they give you is the product of two integers. The product of two integers is negative, okay? Now remember, the given is always true according to our definition of counterexample. We must keep the given statement as true, okay? Then the conjecture that they give me though, which could be false, doesn't mean it is one of the integers is negative or must be negative. So let's see what they're talking about. Okay, so the product means when I multiply two numbers, it's negative. The answer is negative. So meaning when I multiply two numbers, my answer is negative. Well, hopefully you should know the rules of multiplying positive and negative numbers. Think about it to yourself. How do you multiply two numbers that when it comes out gets me negative? Well, the only way that this could be is that if one of them are negative. And let me emphasize on the word only one of them are negative. Okay? And that's kind of what it says here in the conjecture. It says that one of the integers must be negative. So yes, this is an actual true statement. The conjecture is correct. One of the integers must be negative so that the other one's negative. If they're both positive, then obviously that can't get you a negative product or a negative outcome. So in this particular case, we don't need to write out a counterexample. We can just say the word true, okay? I'm gonna do one more from the printed notes, okay? And I'm pretty sure that some of you are gonna pick this up after a bit. Some of them are gonna be a little bit more obvious than others. So this one says, the given statement, it says a polygon has 4 right angles. And we talked about that a right angle is 90 degrees, okay? Now the conjecture that they already give us, remember we're not making any of these conjectures. The conjecture that they give us already is that the polygon must be a square. So that's a key word, must be a square. So again, the given has to always be true, okay? So we have a shape with 4 right angles, okay? That means that the polygon or the shape, the closed figure, must be a square. So you have to think to yourself, right? Well, a square, yes, it does have 4 right angles throughout. Okay, I didn't draw a perfect square, but you get the idea. It's a perfect, all 4 sides are equal, all the angles are 90 degrees. Yeah, you know what? This is true. However, is a square, does it have to be? Is it a must that it has to be a square? In other words, is a square the only shape out there that has 4 right angles? It does not, right? We also have a rectangle, right? We also have a rectangle, even though my drawings are not perfect, I apologize. We know that a rectangle also has 4 right angles. So you know what? We have a counterexample here, meaning we have a false example. Because this is not fully true. It's not that it must be a square, right? You can maybe say the polygon can be a square, then that statement would be true. But because the word must is making it seem like only a square can be the only shape with 4 right angles, which is not true. So the counterexample here is false, and we can say a rectangle also has 4 right angles. So hopefully you're getting the groove of what is a counterexample in this case. I do have one more. We're actually done with lesson 2.1. And this is one that I'm gonna make up. It's gonna kind of seem funny, okay? So don't mind me kind of like writing it out like this. So here's how it goes. The given statement here is a German Shepherd. A German Shepherd is a dog. Okay, a German Shepherd is a dog. Now, the conjecture that you can make about this maybe, or a statement that someone would be able to make, is a dog is a mammal. Yes, I am aware that this has nothing to do with math, but the whole point is to understand how this works. So a German Shepherd is a dog. Remember, that's the statement that we know for sure is true, and the conjecture could be off. So a dog is a mammal. Now, I don't know about you, but I don't know about a dog being anything else but a mammal. Dogs are warm-blooded. They have natural births. You know, they're very similar to cats and humans in the sense. But I don't think it's a reptile. It's not an amphibian. It's not a fish. So yeah, you know what? A dog is a mammal. That is something that we can conclude about a German Shepherd, okay? So, and to be more exact, I can actually put the word German Shepherd here. So let me write that here. A German Shepherd is a mammal. Yeah, you know what? A German Shepherd is a mammal. This is true. I don't need to write a counterexample here. So that's how counterexamples work. On this video, we were able to see the definition of a counterexample as well as the definition of conjecture and inductive reasoning, which you'll see all throughout your homework on lesson 2.1.